No.
Okay, so the sheet that I gave you was getting solo of kinetics. So, and this time we have two big units to cover. Kinetics and thermodynamics, okay? And they're related in terms of how temperature affects reactions and that kind of thing. So, and then that will basically take about 6 or 7 weeks to get through all of that. Those two big units. And then at the end, because the vast majority of taking the test, I have a unit that's kind of like, it's not conceptually difficult, it's more memorization things. It's like what we call intermolecular forces. And it's kind of a review of gas laws and some basic things that aren't conceptually difficult, but that's more, hey, I want that fresh in your mind before you take the test, because that's just more vocabulary kind of thing. So those are the two big things that we have left. What date are the seniors done? May what? 14. May 14? Okay.
No, the third.
It's the
Our last
12th.
graduation's the 13th. Yeah.
Our last day is the 12th.
Or basically, I think we have 7.5 weeks.
So I don't think that May 7th and May's graduation are the same day.
They're not.
So
But all the seniors would be done on the same day. I think
I think
that,
it's
is that that Tuesday?
Yeah, that's our last day.
That Tuesday, May 12th?
Yeah.
Okay.
You gonna come watch us for
Like
it?
in class.
Yeah.
Yeah.
Wait, Brooke can't.
Wait, are you one of the readers?
Huh?
Or do you read the names?
Usually I am.
Do you request a group of the alphabets?
Typically, they always make me go first.
Darn.
Now, it used to be, here's something that the city council wants to fight this
I
fight.
heard about this.
Yeah, it used to be where if you knew who the readers were, that kids could go and sign up for a particular, like, you wanted me to read your name. Oh, there'd be 20 kids that I would read their names. Okay, and kids could sign up for that. But then they shifted and said, oh, you have to go in alphabetical order. So I like that because I was getting kids that I knew, that I had a connection to.
Yeah.
And I would argue, like, what difference does it make what sequence kids are in? So,
Mr. Rankins told us that they stopped doing that because some teachers complained that they never got.
Sounds like a personal problem.
what to tell you?
Or camp. Do we have to keep coming to class? Yeah.
Here's my attitude that I do. You don't bother me, I don't bother you.
Okay.
So if your parents call you out, they call you out. But we're not going to agree in academically
Okay.
relevant.
That you're actually gonna have a
Because the
second
seniors will be
final.
done. The AP test. So
There's no point.
Yeah, not a lot there. I mean, I'm not going to prepare an entire lecture in a minute just for. And you will
That's
probably
okay.
get 2 reasons.
I don't want it.
See, it's a win-win.
Yeah.
Okay. All right. So. All right. So this unit on kinetics, there's a couple of things that are different in terms of how we view this. One is that you look at what is all going to be about rates. Okay. So when you look at different chemical reactions, some reactions take place very, 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 very quickly. Like you all have seen a hydrogen balloon explode. Okay, put the flame to it, bam. Okay, it happens really, really rapidly. So a lot of times what we'll talk about is a graph of time and then concentration. Okay, typically that's going to be measured in molarity. So just like for those of you that have had physics, you can have like a position time graph. Okay, and for those of you that haven't, here's the short version. The position time graph just shows you where you are as a function of time. Okay? And so the slope of this is in meters and this is in seconds. So you can have a very shallow line which means that you're moving very slowly, okay? Because the slope of this line, if you look at the units, are in meters per second, because it's changing y over change in x. Cool, right? So it's a very shallow line. That means that you're not moving very fast. Your position isn't changing very much as a function of time. If you have a very steep line, it's just the opposite. Oh, you're moving quickly because in a short amount of time, you're going to travel a greater distance. So the slope of that line shows you how fast you're moving. And this is going to be important, if it's a curved line like this, and this is harkens back to your days in geometry, you can draw tangent lines, okay? And if you remember, tangent lines only touch a line at one particular point. And so if it's a curved line, that means that the velocity is changing. It isn't constant. But if you want to find what a velocity is at a particular point in time, what's called the instantaneous velocity, you draw a tangent line. And that slope of that tangent line tells you how fast you're going at that instant. Okay? So we can do the same thing with concentration versus time. But the concentration is going to be in molarity instead of meters. Right? And time is typically going to be in seconds. So you could have a situation like you might start off with a very high concentration of hydrogen. Okay, there's the boron. You got hydrogen, where you got a lot of it. Now, hydrogen and oxygen combine to produce water. So if all you have is hydrogen and oxygen, you don't have any concentration of water. But as soon as you ignite it, oh, here's what's going to happen. What's going to happen to the concentration of the hydrogen once you ignite it? It's going to go way down, and it's going to go down rapidly, okay? So the concentration of the hydrogen is going to drop quickly. But at the same time, what are you making? Water. So the concentration of the water would go up, okay? Now, that happens in a very, 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 very short amount of time. And a lot of reactions take place very quickly. You know, you look at the redox unit. Okay, hey, you all did the reaction between potassium permanganate and Fe2 plus. And oh, you did, you know, when you titrated that and you had that Fe2 plus solution and you added that potassium permanganate to it, it isn't like you put in a drop and you had to wait 5 minutes for the reaction to take place, right? That happened almost instantaneously. So a lot of reactions that we study have very, 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 very fast reaction rates, which means a graph of these versus time tends to be very, very steep. Now, you also have reactions that take a while. So here I've got a piece of copper, and down, and I'm going to add some silver nitrate to it. Okay. So first off, here's what you've got, and this is where redox meets kinetics, right? So you've got silver ions placed in the solution of copper. So what's going to happen? Okay, so if you do the over-under game, you're going to make Cu2 plus and elemental silver, right? So if you balance this out, you got 2 here, you got 2 there. So if you can see this, even that's starting to turn slowly into a silverish color. Okay, so that's why I left part of that copper up above, and then I've got that other solution down below. So if you were to look at this again in terms of a graph, and so we had 2 different ions that we're going to talk about. We're going to talk about copper ions, and we're going to talk about silver ions. So as a function of time, what's going to happen to the concentration of the silver ions? it's going to go down because they're being consumed. Now, it's happening, but it's a relatively slow thing. It isn't like, bam, all of a sudden we're done. Boom, it's over. Okay? So over a period of time, I'm going to make more and more and more silver, but the reactions can take a while. So as a graph, the silver ion concentration is going to go down, and the copper ion concentration is going to go up. Okay? So I'm going to produce, because I'm producing more and more copper ions, and I'm decreasing the concentration of the silver. So the biggest thing with kinetics is that when you look at this in terms of rates, any rate, okay, in terms of kinetics, it's a rate function. It's like velocity, but instead of meters per second, any rate function is going to be molarity per second. Sometimes if it's a really slow reaction, it might be like molarity per hour, or sometimes molarity per day, but that's kind of rare. So typically, 99% of the time, the units are going to be molarity per second. Now, sometimes you might see something like micromolarity per second or millimolarity per second. Doesn't matter. It's still the same idea. So here's what's going to happen is that typically what's going to happen is you're going to have one thing being consumed and something else being produced. Typically, though, all you worry about are those that you can actually measure the molarity of. So one of the things like you won't see in this reaction, we won't keep track of the molarity of the copper and the silver because we can't measure that concentration because they're solid. So in terms of expressing these values, all you're going to worry about are things that can be measured in terms of molarity. Now, sometimes, and we'll get into this later, you can deal with gases. So in gases, you could talk about pressures, typically measured in atmospheres. So you can see it expressed in terms of pressure, you can see it expressed in terms of concentration, but you don't worry about the solids. Now, here's the other leap of faith that happens, is that sometimes reactions can be reversed. Now, none of the reactions that we've studied so far can be reversed. Like reactions go in one direction. Like hydrogen and oxygen are going to go in one direction. Okay? We are not going to reach an equilibrium where, the water will start to decompose and react back to produce hydrogen and oxygen. Magnesium reacts with hydrochloric acid. That only goes in one direction. Boom. Okay? But some reactions can reach a point of equilibrium, and there's different things that affect that. So, Mara, bring back, you on the camera, let's go back for a second.